Hello everyone, my name is Krizal Khatka, student ID S385427. Along with my teammates Kusum and Neeraj, we are presenting our project titled Predicting Customer Churn Using Machine Learning and Deep Learning. In this project, we developed and compared various AI-based models to predict whether a telecom customer will leave the company, which we refer to as a churn. The main goal was to identify key patterns that can help businesses reduce customer loss and improve retention strategy. Let's start with the introduction and motivation behind this study. The goal is to predict whether a customer will churn based on factors such as their demographics, service details, and contract information. Our motivation is simple. Reducing churn is crucial for telecom companies because retaining customers is cheaper and more sustainable than acquiring new ones. With the help of machine learning and deep learning, we can efficiently detect early signs of customer dissatisfactions and take proactive action. For development, we used Python with libraries like Pandas, TensorFlow, and SAP for explainability. The models we implemented include decision tree, random forest, naive and a multi-layer artificial neural network. We used the Kaggle Telco customer churn dataset, which is popular and well-structured dataset for churn prediction. It contains 7,043 customer records and 21 columns. The features include demographic details, services used, contract type, and total charges, while the target column is churn, which is labeled as yes or no. This dataset was ideal for our analysis since it provides a diverse range of customer behaviors that can be used to train both traditional and deep learning models. Before we train the models, we performed several pre-processing steps to clean and prepare the dataset. First, we dropped the customer ID column since it didn't provide any useful information. We then converted the total charges column into numeric form and handled missing values. And after that, categorical variables were encoded using both binary and one-hot encoding. The senior citizen column was also converted into a categorical variable for consistency. We scaled all numerical columns using standard scaler to standardize the feature range. And finally, we split the data into 70% for training and 30% for testing. So these pre-processing steps ensure the dataset was cleaned, balanced, and optimized for model performance. Next, we performed exploratory data analysis, starting with churn distribution. As we can see in this bar chart, around 26% of customers have churned, indicating a class imbalance in the dataset. This means that most customers stayed with the company while a smaller portion left. Such imbalance can cause the model to be biased toward predicting no churn. So techniques like resampling or class weighting are often applied to handle this issue. This slide shows the correlation heat map among the different variables. The red areas indicate strong positive correlation while the blue areas shows negative correlation. We observed a moderate correlation between tenure, monthly charges, and total charges, which makes sense since long-term customers usually have higher total charges. Apart from that, most features show low correlation, meaning there was no significant multicollinearity and the dataset was suitable for model training. We also analyzed the distribution of numerical features such as tenure, monthly charges, and total charges. Tenure. Most customers are either new or long term, with fewer in between. Monthly charges. The majority pay lower monthly fees, while only a few customers pay for higher type plans. Total charges. This is skewed towards lower values since many customers are still relatively new. Overall, the company has many low-paying new customers and a smaller group of high-value long-term customers. So here we analyze churn by contract type, focusing on 2-year contracts. We found that customers without long-term contracts had a much higher churn rate, while those with 2-year contracts rarely churn. This shows that long-term contracts help retain customers and reduce churn. So the insight here is that longer contracts lead to stronger loyalty and lower churn risk. Finally, we looked at churn by internet service type, especially fiber optic users. Customers using fiber optic service showed a significantly higher churn rate compared to others. This may suggest that fiber optic users are leaving to due to service quality issues or higher cost compared to DSL users. Those insights are useful for telecom providers to focus retention efforts on customers most at risk of leaving. To summarize my section, we explored the dataset and cleaned it and performed exploratory data analysis to understand the main drivers of a churn. The findings highlight the importance of contract type, internet service quality, and tenure in predicting customer behavior. Thank you.
The next step is feature engineering. First, we improved our dataset so that the model could perform better. We created a new feature called average charges per month. Think of it like this. If one customer has been with the company for 2 months and another for 20 months, just looking at the total charges is not fair. By calculating the average charges per month, we can compare them fairly, like comparing how much someone spends per month rather than the total bill. Next, we group customers based on their tenure into three categories: new, mid-term, and long-term customers. By grouping them, the model can understand patterns specific to each group. Finally, we can standardize numerical features like monthly charges and total charges. Standardization has helped the model to learn evenly from all the features. In short, this step made our data fair, comparable, and ready for the models to learn effectively. After preparing the data, we used both machine learning and deep learning models to predict the churn. On the machine learning side, we used three models: decision tree, random forest, and naive Bayes. Decision tree is a simple model that splits the data based on the important features. Random forest is a group of many decision trees working together to give the better prediction. Whereas naive Bayes is a probabilistic model that is very fast, works well for the first analysis. And for the deep learning, we have used artificial neural network, which works like a human brain, learning complex pattern from the data. We evaluated all the models using the matrices like accuracy, precision, recall, F1 score, and ROC curve. This ensures we are not just looking at the overall correctness, but also how well we detect actual churners. In short, using both ML and DL model allowed us to compare simple and neural approaches on the same dataset. Now let's look at the decision tree first. The decision tree achieved an accuracy of about 71%. Looking at the confusion matrix, it correctly identifies 170 churners out of 373 churners, but missed 203. For non-churners, it predicted 831 correctly and misclassified 205. This tells us that the decision tree does well for the non-churners but misses almost half of the churners. Precision for the churner is 0.45 and the recall is 0.46. That means it's not perfect in catching the churners. The main advantage is that it is very too easy to interpret. We can exactly see which features has driven the churn. However, it can overfit, which means it works well on the training data but not always on the new testing data. Next model is random forest, which performed the best with around 80% of the accuracy. From the confusion matrix, it correctly predicted 177 churners and missed 196. For the non-churner, it got 946 correct and misclassified 90. Random forest is like having a team of trees. Each tree makes a prediction and the majority vote is taken as a final answer. Its best parameter were entropy as a criterion and maximum depth of 10 and 150 trees. This model reduces overfitting compared to the single tree. It also has a balanced precision and recall, meaning that it can correctly identify both joiners and non-joiners. Imagine asking a group of friends for the advice instead of just one person. You get a more reliable answer, right? That's what random forest does. In short, it's robust, stable, and gives the most accurate prediction among our all the models. And next, finally, we have naive Bayes, which achieved around 68% of the accuracy. Naive Bayes use probabilities to predict the churn and assume all the features are independent. While this assumption is not always true for the telecom data, the model still works surprisingly well. Looking at the confusion matrix, it correctly predicted 329 churners out of 373 and missed only 44. For non-churners, it got 625 correct but misclassified 411. It has a high recall, meaning it successfully identifies many customers who actually churn. However, it tends to make more false positive, predicting churn for some customers who do not actually leave. The main advantages of this model are that it is very fast, computationally light, and easy to interpret. This makes it suitable for the large-scale application or as an initial screening model. In short, it's a simple and efficient baseline model, even if it's not the most accurate one.
Now moving on to artificial neural network ANN, the model achieved an accuracy of 0.81. This means that overall 81% of the predictions were correct. One of the strengths of ANN is its ability to capture complex customer patterns. While there is a slight overfitting, the model does a great job at generalizing. Compared to other models, the ANN delivered the highest accuracy, making it top performer in this case. Now moving on to feature selection and interpretability. The top predictors of churn are average charges per month, total charges, and phone service. Service uses patterns like multiple lines, no phone service, and paperless billing strongly influence churn. Demographic features such as gender, senior citizen, dependents have little impact. Shorter tenure slightly increases churn risk. Now, moving on to SAP explainability. This method helps us understand the individual contribution of each feature in predicting churn. Key findings are 2-year contract type and longer tenure significantly reduce churn risk. High monthly charges, fiber optic internet, and electronic check payments increases churn risk. Support-related features like tech support and online security are linked to lower churn. In this analysis, we focused on optimizing machine learning models using cross-validation and hyperparameter tuning. First, we used grid search CV for decision tree and random forest models. For the decision tree, the best accuracy achieved was 78.6%. For the random forest, we got a slightly higher accuracy of 80.1%. For the naive Bayes model, we used a five-fold stratified cross-validation which achieved accuracy of 65.9%. In the model comparison table, we compared four models such as dysentery, random forest, naive Bayes, and ANN. We compared the accuracy, precision, recall, and F1 score. Key insights of this table are ANN had the highest accuracy, 81%, and precision had 67%. Random forest achieved a good balance of precision and recall. Naive Bayes performed well in recall, but with lower precision and accuracy. In conclusion, the best performing models in our analysis were random forest and ANN. The key features influencing the model's predictions were contract tenure, internet service, and monthly charges. From business perspective, We can leverage this information to offer discounts or improve contract options to enhance customer retention and satisfaction. For future work, I recommend experimenting with additional models like KNN, SVM, and XGBoost, as well as techniques like SMOT for balancing data and LSTM and GRE for potentially better performance. Thank you very much.